Hey guys, so today, or actually this week, we are wrapping up probability and statistics, which is super duper exciting. As of right now, we have 2.5 weeks left of school. So this week we're going to do probability and finish it up. Next week we might move into some 8th grade material just to introduce you guys for next year, and then we'll take a final exam, and then it'll be summertime. So let's finish strong. The title is Probabilities for Compound Events. We are on page 61, and the standard is 7 SP 3.8. Okay? So we have 5 different problems we're going to solve today. Compound events. We started compound events last week. So just a reminder, a compound event is 2 or more events. All right, and we began last Friday doing our tree diagrams to talk about how many possible outcomes there were. Our sample space, possible outcomes. So we're going to add on today by not just doing the sample space for compound events using tree diagrams, but we're going to be calculating probabilities. All right, Miss Fry went shopping to get her mom a plant for Mother's Day. At the gardening store, there were 4 different kinds of plants. So we have 4 different kinds of plants. We got tulips, ferns, cacti, and daisies. So those are 4 types of plants. We also have 4 different kinds of pots to put the plants in. We have clay pots, plastic pots, metal pots, and wood pots. Okay, so events isn't like a birthday party. It could be, but it's not usually in statistics. So one of our events is the kind of plants, and then the second event is the kind of pots. So then the question says, if she randomly, oh, we love that word randomly, that's good, picked the plant and the pot, what is the probability that she won't get a metal pot or a cactus? All right, so I'm going to Walmart or Home Depot, gardening store. All right, they have 4 different kinds of plants and 4 types of pots. We want to know the probability that when I randomly pick the plant and the pot, I'm not going to get a metal pot or a cactus. So for compound events, we need to draw tree diagrams. Okay, so the first, branch, I guess, is the base. So it's the kinds of plants. All right, we have tulips, ferns, cactus, daisies. So this is event 1, the type of plant. All right, now event 2 is the kind of pot. So the tulips, if I get tulips, they can go in a clay pot, they can go in a plastic pot, they can go in a metal pot, and they can go in a wood pot. If I get ferns, they can go in a clay pot, they can go in a plastic pot, they can go in a metal pot, or they can go in a wood pot. If I get a cactus, it can go in a clay pot, it can go in a plastic pot, it can go in a metal pot, or it can go in a wood pot. If I get daisies, they can go in a clay pot, They can go in a plastic pot, metal, or wood. And no, it does not matter if we put clay, plastic, metal, wood here, and then put tulip, fern, cactus, or daisy for each one. So event 1, the different kinds of plants. So I put those in pink. Event 2, the different kinds of pots. I put those in light purple. So how many outcomes do we have total? Well, let's count. We have tulip in a clay pot, so tulip, clay. Tulip in a plastic pot. Tulip in a metal pot. And tulip in a wood pot. We have fern in a clay pot. Fern in a plastic pot. Fern in a metal pot. Fern in a wood pot. Cactus in a clay pot. Cactus in a plastic pot. Cactus in a metal pot. Cactus in a wood pot. Daisies in a clay pot. Daisies in a plastic pot. Daisies in a metal pot. Or daisies in a wood pot. So, total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 possible outcomes. Okay, so that is what we learned. This is what we learned how to do on Friday. And thank you for the few of you that actually watched the video and turned in your extra credit. So we have 16 possible outcomes for the kinds of plants and the pots. Now, what is the probability that we're not going to get a metal or a cactus? I don't want metal and I don't want cactus. Okay, so let's look. So what I do is at first I'm like, well, okay, cactus, if I don't want a cactus. So cactus, all 4 of these are cactus. This is cactus clay, cactus plastic, cactus metal, and cactus wood. So I don't want any of those 4. Okay. Tulips are fine, ferns are fine, daisies are fine. Okay. But I also don't want a metal pot. So tulip in a metal pot, not okay. Fern in a metal pot, not okay. Cactus and metal, we already canceled it out because it was a cactus. And then daisies and metals, not okay. All right. So let's count how many how many options I still have left. Tulip and cactus. Oh my goodness, no. Tulip and clay. Yeah, that's good. Tulip and plastic. That's fine. That's not cactus or metal. Tulip and wood. Good. Fern and clay. That's fine. Fern and plastic. Okay. Fern and wood. None of these 4 are okay because those are all cactus. Daisies and clay, that's fine. Daisies and plastic, that's fine. Daisies and metal, no. Daisies and wood. So I circled 1, 2, 3, 4, 5, 6, 7, 8, 9. So the probability of not getting metal pot or cactus equals 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 good ones that I can get and be happy out of how many options total? 16. 4, 8, 12, 16. So 9 out of 16. Okay? So the initial step, you gotta draw the tree diagrams. Gotta draw it. All right, question 2. My brother is moving to California with his family for a new job. True story. In the morning, he has 3 transportation options. 3 transportation options. That's going to be event 1. We have our bus, ride with a friend, so like carpool, or take a train. Okay, so that's event 1. Let's just put event 1 down right now. He can take the bus. He can ride with a friend. Or he can take the train to work. Okay, so on his way to work in the morning, his 3 transportation options: bus, ride with friend, or train. That's in the morning. Okay, and in the evening, he has the same 3 choices for his trip home. So, our first event is how he gets to work in the morning. Bus, ride with friend, train. Then in the evening, he has the same 3 choices. But he doesn't have to pick the same one that he took in the morning. He can take the bus in the morning, and then he can take the bus in the evening. He can carpool with a friend, or he can take the train in the evening. So he has choices. He can ride with a friend in the morning, and then take a bus home, ride back with the friend, or take a train home. Or he can take the train in the morning, take the bus home, ride with a friend, or take the train again. They all have different schedules. The friend leaves at one time, the bus has its own schedule, and the train has its own schedule. But those are his options. So, we have bus in the morning, bus in the evening. So I'm just going to write my options over here. We have bus in the morning, bus in the evening. Bus in the morning, friend in the evening. Bus in the morning, train in the evening. Friend in the morning, bus in the evening. Friend in the morning, friend in the evening. Friend in the morning, train in the evening. Train in the morning, bus in the evening. Train in the morning, friend in the evening. Train in the morning, train in the evening. Okay, so total we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 possible outcomes. Okay. Now, what's the actual question asking us? If Christopher randomly chooses his ride in the morning and in the evening, randomly, what is the probability that? What is the probability that? A. Okay, so let's say part A. What is the probability that he'll take the same mode of transportation twice? So like bus in the morning, bus in the evening. Train in the morning, train in the evening. Friend in the morning, friend in the evening. Okay, well, let's count. Bus, bus. Okay. So bus, bus. Bus, friend. No, that's not the same. Bus, train. That's not the same. Friend, bus. Not the same. Friend, friend. That's the same. Friend, train. No. Train, bus. No. Train, friend. No. Train, train. So 3 of the outcomes are the same in the morning or the evening. Bus and bus, friend and friend, train and train. 3 out of how many possible outcomes were there? 9. So the probability is 3 out of 9. Perfect. Or you can simplify it. 3 divided by 3 is 1. 9 divided by 3 is 3. So there's a 1/3 chance. 1 out of 3. Just leave it as a fraction. I mean, of course, you can always do let me turn that down a little bit. Of course, you can always do 3 divided by 9 or 1 divided by 3. And put that and just say it's 0.33 for the probability, or times it by 100 and say it's a 33.3% chance. I just like to leave it as a fraction. It's the easiest, it's the most accurate in my opinion. All right, let's go on to number 3. This girl looks so creepy right here, this girl in this makeup that I have. Okay, number 3. If you roll a fair 6-sided dice, two fair 6-sided dice. Sorry, I'm so thirsty. Woo! If you roll 2 fair 6-sided dice, so you have 2 dice, okay? 1 through 6 for each. You roll 2 of them. What is the probability that? So we can make a table of all the possible outcomes. You can roll a 1, a 1, a 1, a 2, a 1. There's so many. Okay, so I posted this for you guys to use. So I printed it out. Obviously, I would have handed this out to you guys. But, so the first one is in, I don't know if you want to call that red or orange or orange or whatever red and orange is mixed together. The first, so we have 2 different dice, 2 different die, okay? 2 dice. Solo is die. So the first one, you roll a 1. The second one, you roll a 1. The first one, you roll a 2. The second one, you roll a 1. The first one, you roll a 4. The second one, you roll a 5. Okay, so the first die is the red ones. The second die is the green ones. So these are all the possible outcomes if we made a tree diagram or if we made a chart. I'm trying to think. 1, 2, 3. We could make a tree diagram. That one's going to take really long, though. We could. No, you know what? We're going to use the chart. I like the chart. Okay, so A. What is the probability that the sum, what does sum mean? Sum means add. Sum means add. What is the probability that the sum is 9 or higher? So when you roll both dice, you add up the numbers on both. That when you add them up, they're 9 or higher. Okay? So I'm going to basically just, do I have a colored pencil? That'd be dope right now. I'm going to use a yellow pen. I'm going to color in the ones that when we roll them and add them up, they're 9 or higher. 1 plus 1 is 2. No. 2 plus 1 is 3. No. 3 plus 1 is 4. No. 4 plus 1 is 5. No. 5 plus 1 is 6. No. 6 plus 1 is 7. No. So none of these are 9 or higher. 1 plus 2 is 3. No. 2 plus 2 is 4. No. 3 plus 2 is 5. No. 4 plus 2 is 6. No. 5 plus 2 is 7. No. 6 plus 2 is 8. Nope. Wow, none of these are 9 or higher. 1 plus 3 is 4. No. 2 plus 3 is 5. No. 3 plus 3 is 6. No. 4 plus 3 is 7. No. 5 plus 3 is 8. No. 6 plus 3 is 9. Yes! Yes! That's 9 or higher. Okay. That's our first one. Okay. 4 plus 1 is 5. 2 plus 4 is 6. No. 3 plus 4 is 7. No. 4 plus 4 is 8. No. 5 plus 4 is 9. Yes, it's 9 or higher. 6 plus 4 is 10. 9 or higher. 1 plus 5 is 6. No. 2 plus 5 is 7. No. 3 plus 5 is 8. No. 4 plus 5 is 9. Ha ha ha. 5 plus 5 is 10. That's 9 or higher. 6 plus 5 is 11. That's 9 or higher. 1 plus 6 is 7. No. 2 plus 6 is 8. No. 3 plus 6 is 9. Yes, that's 9 or higher. 4 plus 6 is 10. Yep, that's 9 or higher. 5 plus 6 is 11. That's 9 or higher. 6 plus 6 is 12. That's 9 or higher. So, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, 10 of our, where can I write this? I'm going to do it right here. A. So we had, so what's the probability of that the number is going to be greater than or equal to 9? So greater than or equal to. Or equal to, so it can be 9 or greater than, higher. So it's 9 or higher. Well, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 were 9 or higher out of how many total? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 6 is 36. So there are 36 rectangles here if we counted each possible outcome. So the probability is 10 out of 36. Remember, 10 out of 36. So that's 10 divided by 36. 0.277777, or basically 27.7 repeating percent. Okay. Then we have part B. What's the probability now if we roll 2 dice, that both dice, both of them show an odd number? Odd number. Okay, so we're just going to start with a new one. Both are odd. 1 and 1, yes. Both of those are odd. Remember, odd numbers. 1, 3, 5, 7. Keep going. Okay, 2 and 1, no, 2 is not odd. 3 and 1, yes, those are both odd. 4 and 1, 4 is not odd. 5 and 1, yes, both of those are odd. 6 and 1, 6 is not odd. Okay, 1 and 2, no, 2 is not odd. 2 and 2, no, 2 is not odd. 3 and 2, nope, 2 is not odd. 4 and 2, nope, 2 is not odd. 5 and 2, nope, 2 is not odd. 6 and 2, nope, 2 is not odd. 1 and 3, yes. 2 and 3, no, 2 is not odd. 3 and 3, yep. 4 and 3, nope, 4 is even, not odd. 5 and 3, yep. 6 and 3, nope, 6 is even. I'm kind of noticing a pattern. It looks like it's every other one. Let's see if that's true. 4 is even, so no. 4 is even, so no. 4 is even, so no. 4s are even, so no. 4 is even, so no. 4s are even, so no. Interesting, okay? So 5 and 1 are odd. 5 and 2, nope, 2 is even. 5 and 3, yep. 5 and 4, nope, 4 is even. 5 and 5, yep. 6 and 5, nope, 6 is even. 1 and 6, nope, 6 is even. 6 is even. 6 is even. 6 is even. And 4, 6 is even. 6 is even. So the probability both are odd is, well, how many were both odd? 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of how many outcomes or options or combinations total? 6 by 6 is 36. So 9 out of 36. So which one's more likely? 10 out of 36 or 9 out of 36? 10. Because this one's about 27, 28%. Whereas 9 out of 36, 9 out of divide 36 times by 100 is 25%. 27% is more likely. All right, our last two problems. Mikey, he is shopping at Under Armour for some new clothes to wear to football practice. They have some new technology that dyes your clothes while you wait. Interesting. All right. He gets to pick from 4 pieces of clothing. All right, so that is our first outcome. 4 pieces of clothing. 4 pieces of clothing. So what are those 4 pieces? We got shirt, shorts, pants, or socks. So that's our first event. So we have shirt, shorts. I'm going to write small. I should have not glued the next one so close. Pants, socks. That's event 1. So it's the 4 types of clothing. Okay. Then we have event 2. They come in 3 different colors. 3 colors. We have blue, orange, or green. So the shirt, it comes in blue, orange, or green. The shorts come in blue, orange, or green. The pants can be dyed blue, orange, yep, or green. And the socks can be blue, they can be orange, or they can be green. So let's see how many outcomes we have, just right off the bat. Shirt blue. Oops, I lost my pen that I was using. There we go. So we could get the shirt dyed blue. So shirt blue. We could get the shirt dyed orange. Shirt dyed green. We could get shorts dyed blue. I don't want to use another S. I'm going to do a $sign for this one. Because why not? Shorts dyed blue. Shorts dyed orange. Shorts dyed green. That way I can tell shirts and shorts apart. We could get pants dyed blue. Pants dyed orange. Pants dyed green. Socks. Okay, I'm going to do a cursive S. Socks dyed blue. Socks dyed orange. Socks dyed green. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes that Mikey could create depending on his clothing choice and the color. 12 possible outcomes. Now, let's see what the actual question is asking us, though. Which outcome? So it says, if Mikey randomly picks the piece of clothing and the color, what's the probability that he'll end up with blue shorts? Okay, so shorts and blue. Shorts, blue. That was the $sign blue. Do we have any other one that was shorts and blue? Shirts? No. Shorts, blue, orange, green? Nope, just the shorts, blue. Pants? No. Socks? No. So only one of the 12 outcomes. Only one of the 12 outcomes was blue shorts. 1 out of 12. It's not very likely. All right, our last problem. You flip 3 fair coins. Okay, so we have 3 coins, guys. Each coin is heads or tails. Heads or tails. Heads or tails. Okay, so coin 1. We flip it, we can get heads or tails. That's event 1. Coin 2, we flip it. You can get heads or tails. But you got to do it from each of the first, because that's a second event. But let's say event 1, you got heads. So you get heads for the first flip, then you could get heads for the second, or you could do heads for the first and tails for the second. Tails for the first, heads for the second, tails for the first, heads for the second. We're flipping 3 coins. Okay, so we could do heads, heads, and then heads for the third, heads for the first, heads for the second, tails for the third, heads for the first, tails for the second. So each time you have heads and tails for each option. Okay, let's see our different outcomes. Heads, heads, heads. So we have heads, 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 tails, heads, heads, tails. So you're just following the branches. Heads, tails, heads, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads. I'm getting lost. Tails, tails, tails. So we had 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. 8 possible outcomes. So we want to know, what is the probability that you'll get heads on the first 2 flips and tails on the last flip? Okay, so probability basically of heads on the first 2, so heads, heads, and then tails. Okay, so heads on the first 2 and then tails. So heads, 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 no. Heads, heads, and tails, yes, there we go. Heads, tails, heads, no. We want heads, heads, tails. HHT. HHT, no. Tails, nope. We want heads first. Nope, nope, and nope. So only one of them. Only 1 out of all 8. Now we can prove that. So we know it's 1 out of 8. But let's say we didn't want to draw the tree diagram. Let's break it down. And this is a bit more advanced. So if this confuses you right here, that's fine. You've done enough. Be done. But let's say we wanted to do it without the tree diagram. So we say probability of heads, heads, and tails. So compound events, you multiply the probabilities. So these are our 3 events. What's the probability of getting a heads for the first coin? What's the probability of getting a heads? Well, one side is heads out of 2 sides. Okay? Compound events, we multiply. Let's talk about the second one. Probability of getting a heads. Well, it's 1 out of 2 again. And then the third event, probability of getting a tails. That's also 1/2, because only one side is tails out of 2. 1 times 1 times 1 is 1 over 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So 1/8. That proves it right there. You don't have to do the tree diagram. It's just a lot easier because these other ones, it's just a lot more visual. So, this was a longer video. Thank you for sticking with me. I hope you guys feel more confident about solving probabilities with compound events. And you guys are now capable of completing that Khan Academy exercise.